girl from the Poland, and I will give a talk on the limitation of tensor network approach for optimization and sampling. So please start your talk. So you have a 25-minute talk and a 5-minute discussion. Please start.
Hello. First, let me thank you for your kind introduction and for the invitation. As you heard, I'm here today to talk about limitations of tensor network approaches for optimization and sampling. And that is kind of interplay between employing tensor network techniques in the context of spin glasses, but with the motivations coming from quantum annealing. I've been working on this with Tomek Śmieszchalski and Bartek Gardas from Polish Academy of Sciences, with Marek Grams from Jagiellonian University and Masoud Moshani from HPE. And more details you can read in our paper, which you can find on arXiv. We are witnessing significant progress in the development of quantum simulators. So for instance, a recent paper by Andrew King discusses the simulation of non-equilibrium dynamics. And in this context, it is widely believed that tensor networks are the best classical reference methods. In particular, PEP's tensor network was used there to simulate coherent quantum dynamics. And a few years ago, an algorithm based on the tensor network was proposed to find low energy spectrum of problems defined on the chimera graph. And in that context, tensor network was used to represent classical thermal state and extract information from those thermal states, as opposed to those dynamic techniques. And this approach for a chimera graph was very successful. So we were interested in exploring whether a similar approach based on the tensor network methods can be applied to the new annealing geometries, such as Pegasus geometry and Zephyr geometry. So can it be done? Because Pegasus and Zephyr geometries, like chimera, they are sparse, they are two-dimensional, but they have much higher level of connectivity. And tensor networks work well for low-dimensional problems, I would say up to two-dimensional problems. So the first question we had to ask ourselves was how to formulate these problems so that they are viable to tensor networks. And after encoding the tensor representation of these problems, we had to consider how to contract them to extract information from those tensor networks. And evaluating how those contractions in those cases would behave, it required testing. And at the very beginning, I can say that the application of tensor networks to Pegasus and Zephyr geometries was extremely challenging. And in this talk, I will briefly tell you how we set up our algorithm, and then I will show you the results of the tensor network approach in comparison to the quantum annealer and the classical Ising solver based on simulated bifurcation. So what are the main steps of our algorithm? It is based on a branch and bound algorithm in the probability space. And the branch and bound algorithm allows us to search for low energy states. Because as we claim, the low energy states are the most probable ones. And tensor networks are incorporated into this algorithm at the probability calculation level. So tensor networks are used for calculating probabilities because they represent the classical Boltzmann distribution. And we also tried the option for local dimensional reduction of cluster degrees of freedom using loopy belief propagation. I'm going to elaborate on all of these concepts during this talk. So we are interested in quasi-two-dimensional graphs, which are relevant to current quantum annealing processors, like, as I said, Pegasus graph and Zephyr graph. On this slide, you can see the Pegasus graph on the left-hand side, and the spins are the black dots, and the couplings between them are gray lines. So to apply the tensor network approach, which, as I said, works for low dimensional problems, we have to use those quasi-two-dimensional structure of this graph. So we group spins, which naturally builds unit cells into clusters. And in the case of Pegasus graph, each cluster consists of 24 spins, while for the Zephyr graph, it's 16 spins in each unit cell. This is marked here by those red lines. And after such a grouping, we obtain quasi-two-dimensional structure. You can see it on the right-hand side. And we call it a clustered Hamiltonian. So this means we go from an Ising representation of the problem to a clustered Hamiltonian representation, which is defined on a square lattice with those red nodes, with nearest neighbor couplings, those blue lines, and diagonal couplings, green lines. And the similar approach works for the Zephyr graph. And our goal is to identify low energy states from exponentially many possible spin configurations. And we do this by finding the most probable states, like most probable configurations according to a Boltzmann distribution at some inverse temperature beta. So we claim that finding low energy states is equivalent to finding most probable states according to a Boltzmann distribution. And we use a branch and bound strategy. So we have like the two-dimensional system, those clustered Hamiltonian, and we sweep through those two-dimensional system cluster by cluster. So for example, here we have the configuration of nth cluster, and we want to find the configuration in n+1 cluster. And at each step of those branch and bound strategy, we identify a set of configuration with high marginal probabilities. And we branch these configurations to include all possible values in the next cluster, and we calculate their marginal probabilities. We calculate their probabilities using approximate contraction of the PEPS tensor network. And then we bound the set of those candidate partial configurations. We are doing this in two steps. So first, we use the locality of interactions, and we group states according to their boundary configurations, and we retain only the most probable ones. And discarded probabilities, they encode excitations in the system, and those discarded probabilities helps us to map the low energy spectrum. And finally, we keep only the most probable configurations. In this case, we keep only the m most probable configurations. And this completes a single step of the sweep. And then we move to another cluster. We repeat the procedure. So we continue those branching and the bounding until the final cluster is processed. And this enables us to identify the ground state candidate and the low energy excitations. So to employ those branch and bound algorithm, it is crucial to effectively calculate the conditional probabilities or marginal probabilities. And we represent all probabilities using a two-dimensional tensor network. It is called projected entangled pair state tensor network, or in short, PEPS tensor network. So for a classical system, and we are interested in a classical system, the construction of a thermal state is exact, and it is equivalent to the representation of its partition function. So in our representation, we defined various kinds of tensors. For instance, we have those side tensors and the red circles, and they carry information about the local energies. We also introduced the bond tensors, those squares, and the bond tensors, they encode two-side interactions. And we also introduce mediating tensors, these purple circles. They encode they encode the diagonal interactions in a tensor network. So after such a mapping from the clustered Hamiltonian, which you can see here, we obtain such a tensor network. And this is two-dimensional tensor network, and it is viable to approximate tensor network contraction techniques. Why I am saying that approximate tensor network contraction techniques? Because finding the ground state of a general Ising spin glass problem is NP-hard problem. And in the tensor network representation of a spin glass problem, this hardness manifests itself in the fact that it is even sharply hard or sharply complete to contract the general PEPS tensor network. So to extract information from those tensor network. So it is even higher than NP because it contains information not only about the ground state, but also about the full low energy spectrum. Fortunately for us, there are approximate contraction schemes which we can use, and we employ the boundary MPS approach. So we have to contract the tensors in the gray box. So we take the MPS matrix product state from the previous row, and we can contract it with tensors in the next row. This is a transfer matrix or matrix product operator. And we obtain the matrix product state, but with enlarged bond dimension. And we have to somehow truncate those bond dimension. So after all, we got the matrix product state with limited bond dimension. So if we want to calculate such a probabilities of configuration in F+1 cluster, but we have the information of the configuration in the previous nth cluster, we have to contract such a tensor network. So the lower part of this network is the PEPS tensor network, which we contract using approximate boundary MPS approach. And the rest of the lattice we can contract, let's say, exactly, after all, getting the probability. But our problems are built with large unit cells. As I said, for a Pegasus graph, for a full Pegasus graph, in every unit cell, we have 24 spins. So 2 to the power 24 possible spin configurations. So the tensor sizes needed to encode these problems, they are huge. So it requires dedicated approach, especially for those approximating boundary MPS. So as I said, making it work requires a lot of technical concepts. So what are the key methodologies of our algorithm? First of all, we use the sparse PEPS tensor network structures to efficiently contract tensor networks with extremely large tensor sizes. And sparsity in this context means that we do not have to build those tensors explicitly. We can rather keep them as a building blocks and contract the networks using those building blocks, using the internal structure of those tensors. And we contract the tensor network using batched matrix multiplication. And to speed up computations, we use GPUs. To approximate those boundary MPS, we use variational zipper algorithm, And in this algorithm, as I said, we got the MPS with enlarged bond dimension. So we have to truncate those bond dimensions using SVD. And in our case, we use randomized truncated SVD method because it's more time and memory efficient. However, it can introduce instabilities in the contraction, which you will see in one of my last slides. And we also tried the option for reducing local dimension of cluster degrees of freedom using loopy belief propagation. To test the instances, we use two performance metrics, like the energy metric, the best energy found, and the diversity of identified low energy configurations. So in the energy metric, our goal is to achieve the lowest energy within reasonable available resources. And we will plot it as a relative energy difference above the best known solution, where this E-best is the reference energy established by collecting the results from all tested solvers and selecting the optimal one. In the second metric, we probe the quality of sampling of diverse approximate solutions of spin-glass problems. So our goal is to select from the set of available low energy solutions with energy below a given approximation ratio, the largest set of independent solutions. So independence in this context means that, let's say we have two spin configurations and they are independent if their Hamming distance is above a given threshold, R times N, where R is the distance threshold and N is the system size. So in other words, what do we mean by the diversity, for example, 10? So the diversity equal 10 means that in the set of all states below given approximation ratio, we have found 10 states such that each of them is far from every other state in this set by more than R times N. And apart from the tensor-network-based algorithm, we test all the instances on D-wave quantum annealer. We also use the simulated bifurcation machine algorithm as a second classical solver. So the simulated bifurcation is quantum-inspired algorithm, a heuristic algorithm based on numerical simulation of classical counterpart of a quantum bifurcation machine. So we have to solve Hamiltonian equations of motions, which are differential equations, and solutions are encoded in the steady states. And a solution at the final time is at least a local minimum of the Ising problem. One of the key advantages of SBM is its ability to manage dense spin-spin interactions with high precision. So SBM supports general geometries. Also, SBM can be accelerated by parallel processing, for instance, using GPUs. Now let's move to the results part. So let's start with the ground state search. We tested random instances on the Pegasus and Zephyr graphs. Here you can see the Pegasus graph. The random instances with couplings uniformly distributed in -1,1 and without local fields. But we also tested another classes of instances, like random instances with non-zero local fields or corrupted biased ferromagnet instances for the Pegasus graph. If you are interested, you may take a look on our paper. And apart from the full space tensor network simulations, which here are encoded using those green dots, we also tried the simulations with local dimensional reduction of cluster degrees of freedom using loopy belief propagation, LBP. This is here shown using those red and blue dots. And what those local dimensional reduction means. For instance, for a full Pegasus graph, In each cluster, we have 24 spins, so 2 to the power 24 possible spin configurations. But we can select only the most probable configurations in every cluster, the most relevant ones. So we can truncate the configurations from 2 to the power 24 to 2 to the power 20 or 2 to the power 16. And to do this, we use loopy propagation. And the horizontal axis measures the time of each algorithm, where each point indicates the best solution at the end of the independent algorithm execution with some set termination criterion. And the vertical axis measures the solution quality as a relative energy difference above the best known solution. And you may see that for the smallest Pegasus graph with 216 spins, tensor networks without those dimensional reduction and tensor network with local dimensional reduction to 2 to the power 20 states, they identify the ground state. However, tensor networks with those dimensional reduction, but to 2 to the power 16 states in each cluster, employing those dimensional reduction prevents us from finding the ground states in some cases. And this is due to the fact that the ground state is no longer supported by the reduced set of cluster configurations. In the case of the largest Pegasus graph with more than 5,000 spins, due to the memory limitations, we only performed the calculations with those dimensional reduction. And you may see that for Pegasus graph with more than 1,000 spins and 5,000 spins, the best energies tensor network method identifies they're systematically below the approximation ratio of 10 to the power minus 2. However, we are not able to identify the optimal solution, both with and without employing the dimensional reduction. The solutions from D-Wave and from SBM are similar, let's say. So both QPU and SBM, they find high quality, sometimes optimal solutions at very fast time scales. As for the simulation time, we see that SBM is fairly competitive with D-Wave, and algorithms based on the tensor network, they require orders of magnitude more time. Zephyr geometry, on the other hand, proves to be more challenging to the tensor network approach, so we are able to identify states within approximation ratio 10 to the power minus 1. And this is due to the fact that the Zephyr graph has larger fraction of diagonal interactions than in comparison to the Pegasus graph. And it has its impact on the contraction stability. We also check the quality of sampling in the framework of the diversity of solution. Here I'm showing you the full Pegasus graph with more than 5,000 spins. And we focus on two distance thresholds. Large distance threshold are equal one half, and smaller distance threshold are equal 1/4. And we set the approximation ratio value to 0.01. For R equal 1/2, the average ground truth diversity is of the order of 8, while for the lower distance threshold is of the order of 4,000. And both QPU and D-Wave, they identify all of the diverse solution for the R equal 1/2. Like tensor networks identifies 50% of diverse solution. But for the smaller distance threshold, tensor network obtained less diverse states. It's negligible number of diverse states, negligible fraction, than SBM and D-Wave. And it may be related to the fact that D-Wave machine and SBM generally gives an order of magnitude more states in their result than the tensor network approach. And as we relax the criterion for diverse states. This quantitative advantage translates to more states, more diverse states found by D-Wave and SBM than for the tensor networks approach. The behavior of the Zephyr graph is similar. You may see that for the lower distance threshold, the fraction of diverse states found by tensor networks is negligible in comparison to SBM and D-Wave. And for one of my last slides is to better understand the limitations of our tensor network approach, we want to find the results of contraction instability. So we focused on the smallest problem size for the Pegasus graph with 216 spins, and we ran tests across different values of inverse temperature beta. Here you can see it on the horizontal axis, different bond dimensions and numerical precision settings. And our main goal was to see how often the algorithm finds the ground state. This is shown on the panel A, and the results highlights a general trade-off. So while working with tensor networks, there is always a trade-off between accuracy and stability. So if we increase the inverse temperature parameter beta, the branch and bound method can explore the system more thoroughly, but it makes the tensor contractions less stable. On the other hand, using smaller beta improves numerical stability, but limits how well the algorithm can explore possible solutions. So panel B focuses on the truncation error, but from the panels A and B, you may see that the precision of numerical calculation, for instance, using float 32 or float 64, doesn't significantly impact the results. And panel C shows algorithm instability, where repeated runs sometimes produce different results. And this is linked to randomized truncated SVD, which introduces those fluctuations that the variational optimization, MPS optimization cannot fully correct. And this is the key issue, the key source of limitations of the tensor network approach. So as I'm running out of the time, that brings me to the end of my presentation. So I'd like to conclude with saying that the contraction stability is the biggest issue of the tensor network approach. We also observed that the hardness of contraction grows with lattice connectivity, but quantum annealers are really good solvers, but SBM provides very competitive results. So those parallel tempering or PT plus ICM, they are believed to be the best benchmarking solvers. And in this context, it turns out that SBM work equally well, so it for sure deserves more attention. Our tensor network solver is available online, so you can download the code, you can use it yourself, so please take a look if you are interested. And all of the data is also available online, as well as the preprint. So thank you for listening, and if you have any question, I would be glad to answer.
Yes, thank you very much. Very interesting talk. So any question, comment? Tim, so please.
Yes, the graphs you showed, for how many instances were those? Maybe I missed it. Is it a single instance or an average?
No, it's 20 instances.
Okay, and do you have, well, at those sizes, you have no telling whether they are like hard or easy, right?
Well, those CBFMP instances, they are supposed to be hard for the classical and quantum solvers. There is a paper by TASEV, and the random instances, but those CBFMP instances, they were similar. The performance was similar to the random instances.
Okay,
but it was the
thanks.
20 instances with.
Okay, so any question, comment from audience? So I have a very simple question. So your result is based on the single GPU calculation for the tensor network and the simulated bifurcation machine. So if we use multi node GPU. So then maybe that your result will improve.
Maybe it will improve. Yeah.
So,
Yeah.
did you not didn't you
No,
perform
we
such?
didn't. We didn't try it because we
Yeah.
we didn't have
Okay.
but maybe our results will improve, but time will maybe improve. Yeah, but
yes, of course,
for
yes. Time is yes, but the diversity is not improved, right?
yeah, because the reason of the instabilities is due to those SVD. So if we have better SVD, better those randomized SVD, then the ground state maybe would be better, or the lowest energy would be better. But this is only for single GPU.
Yes. Okay. I see. Good. So, any question or comment?
Yeah, maybe me again if it's no one else.
Yes, please. Yes, okay.
So for the SBM, you take the standard implementation from those papers 2019, 2021, yes? Okay.
Yes, yes.
I'm intrigued that it works as well as the D-Wave. My expectation would have been for hard instance, the D-Wave should be better actually. So interesting.
Yeah, but yeah, it's very interesting for us too.
Thank you, Tim. So, any other question, comment? Okay. If not, time is already up. So let's thanks to the Anna speaker again. So thank you very much for very, very interesting talks. So we are
Thank
very
you.
excited. Yes. Thank you very much. Okay. So
Bye-bye.
see you.